Alright, here's a basic review of some VSEPR shapes. Up here I've drawn just five basic shapes. I'm not doing all of them. I'm just giving you 5 of them. And I also put some letter notation next to each one, and we're going to talk about these letter notations and how they work. So linear is the most basic type. Like CO2, carbon dioxide, is a linear molecule. What's working here, what's going on here is that the carbon is acting like the A and the oxygens are acting like the B's. So over here with trigonal planar, you have the boron acting like A, and boron is a molecule that likes to form 3 bonds. It likes to only have 6 valence electrons around it. And then the fluorines are acting like the B's. Now the exception, or the difference maker over here, it comes when you have E's involved. On that same A molecule, you can have free pairs of electrons. Those free pairs of electrons, for each pair, we call an E. So over here for water, we have A, B, B, so that's A, B2, E2, because we have 2 pairs of electrons. 2 total pairs of electrons. So this would be an A, B2, E2 molecule. So to practice this, let's try SCl2. Again, I'm just going to go really slow with it. So sulfur has normally 6 valence electrons. Fluorine has 7. That's a total of 7 plus 7, 14, 15, 16, 17, 18, 19, 20. That's a total of 20 electrons. So our structure, our Lewis structure that we're going to draw here in a second, and then we'll go to the VSEPR structure. Our Lewis structure is going to have 20 electrons. So you put the least electronegative atom in the middle. In this case, it's sulfur. And then you make your single bonds, and then attach the other 2 guys you got. Follow the octet rule. So sulfur wants 8, it gets 8. Fluorine wants 8, so it gets 8. And so does this guy. Count them up and see if that works, because we're following the octet rule. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. All right, so that's your Lewis structure. That's the proper Lewis structure for SCl2. Now, what about the VSEPR structure? Well, one basic way to start out doing this is to first label the A's and the B's based on that letter notation that we just saw. So sulfur would be your A, chlorine would be your B's, and then you have, in this one, you have 2 free electron pairs, here and here. So each electron pair is an E. So this is technically an A, B2, E2 molecule, because we have 1 A, 2 B's, and 2 E's. Now going back to that chart, so A, B2, E2, here it is. So this guy's bent. This is a bent molecule. And what's happening is that these electrons are pushing down these bonds. Remember, VSEPR stands for valence shell electron pair repulsion. So the electron pair repulsion part is over here, seen here, where you have these 2 electron pairs repulsing, pushing down these bonds. And that creates a different bond angle than you would normally see. So that's just a basic way. So this guy came out to be bent. Let's try another one. Pi3. All right, so phosphorus. Phosphorus has 5 valence electrons. Iodine, 7. We have 3 iodines, times 3. That gives you a total of 26. 26 electrons. And just count them up and you'll get that. So Lewis structure, put the P in the middle. Again, least electronegative goes in the middle. We got our 3 iodines on the outside. Now follow the octet rule. 1, 2. So 1, 2, 3, 4, 5, 6, 7, 8. Phosphorus is good. 1, 2, 3, 4, 5, 6, 7, 8. Iodine's good. Same with these iodines. They all 1, 8. Count them up. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26. We're good. That's your Lewis structure. Okay, so what's the VSEPR structure? Again, you can do the labeling, and this will give you that here's your A, the P is the A molecule, and each iodine is a B. And then again, look for electron pairs. Now, one thing you want to notice is that we only really worry about the electron pairs on the A molecule. We do not worry about the electron pairs on the peripheral molecules, these iodines, on the B molecules. Only worry about the electron pairs on that A atom. So whatever's on the A atom is what you're worried about. So in this case, we're talking about an A, we got 3 Bs, and then 1 A. So what does that correspond to? AB3E, trigonal pyramidal. Same thing, this electron pair up here is repulsing these bonds, pushing them down, creating a different bond angle. And that's PI3. The last one I'll do. SiCl3Br, which is actually a pretty easy one. So silicon right under carbon, so it has 4 valence electrons. Each chlorine has 7, and each bromine has also 7. These guys are halogens, and we have 3 fluorines. So 7 times 4, because again, 1, 2, 3, 4, 5, 6, 7. And then we got 3 sets of 7s here. And then you add 4. That is 32. It is a total of 32 valence shell electrons. Oops, excuse me. It's a total of 32 electrons. That's your magic number. And again, this is just regarding Lewis structure. So drawing this guy out, Si is the least electronegative, so he goes in the middle. And then you put your CLs wherever you want, and your BRs wherever you want. Again, follow the octet rule. You got a lot of dots to draw here. Everyone wants 8. There's no exceptions here. And let me fix this C here. There we go. And Cl. Now notice there are no free electrons on this silicon. No free electrons there. So there's no E's involved here. So this is a molecule that has, here's your A right in the middle, and here are your B's on the periphery. And bromine also counts as a B. Doesn't matter if you have a different atom. So this is an AB4 molecule. And that corresponds to which one? Tetrahedral. So that shape, or the shape for that structure for SiCl3Br is tetrahedral, or tetrahedron.